All right, hello everybody. Welcome back to Physics 110. Today we are going to continue our discussion from the previous lecture, which was introducing circuits. Although we spent a good half of that time talking about electric fields and electric potential, and then we started talking about circuits and Ohm's law. Today we are going to continue that, but we're going to talk about some more complex circuits and then look at some real-life applications. Hello, I've got somebody in the chat. Hi, Kevin. Anybody else who's around and want to say hi, that would be great. But let's go ahead and get started. All right, so the first thing is I'm going to show you guys a couple of videos. I've realized that the link here given was a bad link when I tried to follow it. It's expired or something. So I have new versions. I can add those to the Canvas page if you want to watch these on your own later. Hello, everybody. All right, so let's go ahead and take a look at these. I'm going to expand the window here. Aha, it will work. All right, so here we've got a set of 5 light bulbs, obviously, and they are wired in a very specific way. And what I'm going to do is show this video a couple of times, and I want you to write down, if you can, observations that you make in terms of when are they bright or when are they dim, what happens if you take one out of the circuit. Go ahead, there we go. All right, so there's 1 bulb in the circuit. Now there's 3. Now there's 5. They're going to remove 1 bulb and put it back in. Down to 3 bulbs again, and then down to 1. All right. Okay. So again, I guess you kind of, hopefully you saw it. Well, I'll give you another pass through in case you're writing things down. But this is just one way of configuring light bulbs, like one way to build a circuit. We're going to see another way in the next video. All right, so that's the first way. Now let's look at the second video. So it looks very similar, right? It looks like the same 5 light bulbs, but the way they've been wired together is now different. So let's see what happens this time. Okay, we've got 1 bulb that's on. Now 2 and 3, 4, and 5. Taking 1 out. So let's watch that one again. It doesn't matter if it's muted or not, there's no sound on that. There we go. And then as they remove bulbs from the circuit. Okay. So what we want to do now is summarize what you saw, right? So if anybody in the chat wants to give me some things that they saw, that would be great. I'll give a couple different things that we might think about. What happens when we add more bulbs? and what happens when we take them away. And I've got comments on both of these. I love it. So take bulb away. All right, so this first one, Kevin says the bulbs get brighter when there are fewer resistors. So the other way. So as we add more bulbs, they get dimmer. Or if we have less bulbs, it's brighter. Down here, Frankie says they're able to stay on by themselves. So as we take a bulb away, these stay on. And these are in contrast to each other because when we take away a bulb in the first one, they all turn off. Whereas if we take away a bulb, or if we take the bulb away here, they still stay on. Here, as we add more bulbs, they get dimmer. As we add more bulbs here, they might get slightly dimmer, but like honestly not by much, right? They generally stay bright. So these are two extremely different kinds of behaviors for what looks like the same 5 light bulbs, right? But what matters is how you connect them. How you connect them to each other, how you connect them to the battery. And as you might have seen in the title of the slide or from your reading, this first one is a series circuit, and the second one is parallel. So we're going to talk about each of those, what they are, why they give us these results. Okay. And I'm going to try something this time. This is the kind of thing I would normally leave up on the whiteboard at school so that we could reference it as we move forward, but I don't have enough whiteboard space, so I took a picture, reference that hopefully later. Let's see. Okay. My eraser. Where did it? Oh, I found it. All right. So let's go ahead and do this. Let's first do our series circuit. Okay, so this was like video 1. This is where as you added more resistors, they got dimmer. And as you took any one of them out, all of them turned off. Okay. So the way we organize resistors in series is series means one after another, right? Like if you think about like a movie series like Harry Potter, it's like the movies come out one after another, okay? And so that's what's happening here. We're gonna do one and then the next one, then the next one, then the next one. And you can stack as many resistors as you want in series. We're gonna usually stick to 2 or 3 because that's plenty. But basically, I'm going to use our circuit diagram notation here that I introduced last time that you guys will also see in lab. Speaking of, the lab intro video is live on Canvas, so I really highly recommend that you check that out before you do the lab because I go through an example of what we want to see for some of the tables and graphs that I think will be helpful for you guys. So there you go. All right, this was our symbol for a battery. The long side is positive, the short side is negative. And then we have wires that come out and connect to our resistors. So I'm going to just draw 2 of these because it's easier. And again, if it's a normal resistor like the little peanut guys that I showed you last time, you would just draw it like this. Because we're doing light bulbs, we can go ahead and add our glass circle around it, right? Because a light bulb has that glass sort of shape. And we're going to name these R1 and R2. So again, capital R is the resistance. We measure it in ohms, which we write with the Greek letter omega. And resistance says, I don't want current coming this way, okay? It resists the current. The source, the voltage here from the battery, it gives energy, right? It creates the uphill. So my analogy that I had before was that the battery creates a hill. See that? Where negative is at the bottom and positive is at the top. And when we had only one resistor, that resistor gave us the entire downhill. But now we have two resistors. And so what's going to happen is that we're going to essentially get two different downhills. So this part here is because of R1, and then this part here is because of R2. In other words, we lose some energy across R1 and then the rest of it across R2. So at the top of the circuit here, we're going to match our biggest potential value at the top of the hill that we have here. And then we go downhill a bit, downhill the rest, now we're at the bottom of the hill. But it's like going downhill in 2 steps instead of 1 because we have 2 resistors. That means that if these resistors are different from each other, they can have different amounts of energy drop. We'll see more of that later, a little bit. But importantly, we want to think about what happens with the current. Okay? So again, the current is going to be, in our analogy, it's like we have a ball that rolls downhill. Well, there's just the one hill to go down. It just goes down it step by step, right? One bit after the other. And if we come here, we don't have any breaks. We don't have any other avenues for the current to go through. There's just the one wire, this one, and then the next. So our current, the same amount of current, is going to go through both of these. And that's something you guys will be investigating in lab. Okay? All right. The equation that is listed here is the equivalent resistance of the entire circuit. So the amount of current that comes out here depends on what resistance in total the battery sees. So it's not like it sees only R1 or sees only R2, it feels the effect of both of those. And so when we want to find the effective resistance for the whole thing, for series it's pretty straightforward. We just add these resistors together. So that's not too bad. It'll be a little more complex when we do the parallel circuits, but for series it's okay. So again, the question you want to ask yourself if you're trying to figure out, are these things in series, is you want to say, are there any junctions? Are there any places where this branches off? And if the answer is no, it's in series. All right, let's do some examples. Okay, let's try doing some Ohm's law stuff here. All right, a 9-volt battery is connected to 3 30-ohm light bulbs in series. What is the current in the circuit? All right, so I will calculate this. We've got 9 volts, we've got 3 batteries. So delta V from the battery equals 9 volts. And then R for each of these is 30 ohms. If I draw this, 1, 2, 3 of these, in this case, all of my resistors are the same value, right? And I know up here I have 9 volts, that's positive, and down here is the negative or the low side, so we'll call that 0. Now I want to emphasize what we saw last time, which is that up here, everywhere along the same wire, that's all 9 volts, okay? Whereas, my color coding's on, well, whatever, it doesn't matter. Down here, all of this is 0 volts. So from the top of the first resistor to the bottom of the third, we lose all 9 volts, right? We're going from the top, like 9 volts up here, down to 0 volts down there. But in between, we can and we will eventually figure out how much energy comes across each one, okay? But first, let's answer this question. How much current is in the circuit? So again, the current is going to be the same for all of these. And it's created by the battery seeing this resistance. And so we can use Ohm's law here to think about the entire circuit. Delta V equals IR. And so if we do delta V of the battery here, we're asking ourselves from this top of the 9 volts to the bottom of the 0, how much resistance do we see? So my battery, my delta V is 9 volts. My current, I don't know. And I want to know how much total resistance do I see? Well, I've got 30 plus 30 plus 30. That's going to be 90. So if we divide both sides by 90, we will have 9 divided by 90, which is 0.1 amps. That's the current that goes through. Now, you guys tell me, how much current will there be if there are 2 bulbs instead of 3? Okay. So we're going to have, this is the case in the video where it's still a good circuit, but we have just fewer resistors. So what would you get in that situation? Oh, the question is, Frankie says, what did they all turn off? So what we're doing is we're going to replace one of the resistors with wire. In essence, we're asking about this circuit. We're going to, where it's all connected, just with 2 instead of 3. We will talk about what happens if you just take one out without making it a complete circuit. But we'll assume for now that it is a complete circuit, and we'll see what we get. So Kevin says 0.15 amps, and I agree. Because in that case, we've got 30 and 30 and 9. And so we would take 9 equals current times now 30 plus 30 is 60. And if you solve for the current, it would be 0.15 amps. Okay. So when there are fewer resistors, when there's 2 of them, we get a bigger current. That's going to lead to brighter light bulbs. When we have 3 resistors, we had a smaller one, right? Because 0.1 is smaller than 0.15, so they are dimmer. And that's because resistors resist current. The more resistors you have in series, the more they're like, don't send current to us, no thank you. And so that means you get the smaller current, you get dimmer light bulbs. Now, let's talk about Frankie's point, which is what happens when you just take one out entirely, right? And you don't reconnect it to make it a good circuit. Well, it's not a good circuit. It's not connected. We don't have a full loop anymore. And so that's going to turn off. And it doesn't matter which one you take out. If you take any element out and you don't reconnect it, nothing. No current at all, okay? Because it's not a good circuit. So that's what we saw in the video for video 1. right? See if this works where I bring up the my photo. That's what we had said, right? As we add more bulbs, it gets dimmer because our current is going to get smaller. And if we take any bulb away, they all turn off because we don't have a nice loop. But that was just video 1. Now let's talk about what happens with video 2, which were parallel circuits. All right, so let's draw the circuit diagram first. So we start with our battery, plus and minus side, right? This is, the battery creates the energy, gives us our hill. And then we're gonna come over here and do our first resistor, our first light bulb like this. And then we're gonna draw the next one over here. So these two resistors, R1 and R2, are in parallel. They're in parallel with each other and with the light bulb, or with the battery. And I've tried to draw this, it's traditionally drawn this way, where they look like parallel things, okay? But that's not the best way to identify whether something is in parallel or not. The way to do it is to think about the way they're connected. So here, if we think about what is at 9 volts, right? What is at my top of my battery here? Well, this wire is connected, and then I have a junction. So this junction tells you it's not in series, but it's all connected by wire. Anything that's just wire connected to wire with no other element in between will be at the same potential. All of this is at 9 volts. On the other hand, if we look at the bottom part, down here I'm at 0 volts, and anything along this wire is at 0 volts, like that. And so these are connected. There's a connection point here, and the important thing is that connection point puts them at the same potential on the top of the resistors. And at the bottom there's another connection, and that bottom connection puts them at the same, although different, value, right? It's 0 instead of 9, but they're both 0, just like both of these are 9. That's what happens with the energies when you're in parallel. Let's see if I can draw my hill. It's a little bit trickier. I've got my hill that goes from my negative to positive, and then what I end up getting is 2 different paths to the bottom of the hill. Okay? So I've got, this would be path 1, resistor 1, and this would be path 2, resistor 2. So both of them cover the entire hill, as opposed to one after the other, right? Both of them have the same energy drop, the same voltage across them. But what's really interesting is now you've given the current a choice, okay? When there's only one loop, when there's only one path that the current can take, everything in the circuit has that same current. But now we split it, we give it a choice. So conceivably, you could have a situation where you've got a whole bunch of current that comes down one of these, and then not very much down the other. And that would be allowed, right? Maybe this one has a really big resistance, and it says, don't send current my way. And this one maybe has a really small resistance, and it's like, yeah, sure, I don't mind that much, current can come. And so the current through these can be different, but the potential drop across them is always the same. All right. Now, the unfortunate thing is that the equation to figure out the effective resistance that this battery sees it's going to be more complicated. So it looks like this. 1 over our parallel, and you know what? I don't like writing parallel because I almost always spell it wrong, and it takes me a while. I'm just going to do the parallel lines. It's like the math symbol for parallel. Okay. So 1 over r parallel equals 1 over r1 plus 1 over r2 plus 1 over r3, etc. Because maybe you have more things in parallel. Okay. Let me do an example just of this. Let me just make up some numbers. Let's say R1 equals 20 ohms and R2 equals 5 ohms. Okay, so I have a bigger resistance and a smaller resistance. What I would plug in here is I'm looking for 1 over R parallel, but I'm going to leave it 1 over R parallel to begin with. And then I'm going to plug in, well, 1 over R1 is 1 over 20. Plus 1 over R2 is 1 over 5. This is not, remember when you add fractions, you cannot just add across the top and the bottom. You're only allowed to add across the top if the denominators are the same, which these are not. So you might as well just plug it into your calculator, right? In this case, this should be, we could find a common denominator, right? We could find 20. This would be 4 20s and 5 20s, so it would be 5 20s. I'm going to write it that way. And then I'm going to double check myself to make sure that I'm right, because I'm not that good at fractions. All right, let's see here. 1 divided by 20 plus 1 divided by 5. Maybe if I actually type the numbers in right, that would be better. Yeah, so it gives us 1/4, which is the same as 5 over 20. Okay, cool. But we're not done. We found 1 over our parallel. We want to find now the reciprocal of both sides. So if 1 over r parallel equals 5 over 20, then that tells me that r parallel will be 20 divided by 5. So you flip it at the end after you've already added them. But that will give me a result of 4 ohms. Anything weird about that number 4? How does it compare to 20 and 5? Last I checked, 4 was smaller than either 20 or 5. Isn't that strange, right? If we think about it, if I had put these two resistors in series, their equivalent resistance would be 25, right? 20 plus 5. It's bigger, right? More resistance, bigger. Kevin says 5 times 4 equals 20. Yeah, I think that's a coincidence just because of the way the numbers ended up working out. If I'd done different numbers, it would have been a different result. I'll have to use different numbers next time because these are too nice. The point is 4 is smaller. Okay? 4 is a smaller number than either 20 or 5. So we have two relatively big resistors. We put them in parallel, and the result of that is something smaller than either of them. Come on, that's weird, right? Does that feel a little bit weird? You're getting smaller numbers by combining big numbers. It blows my mind. I love it. All right, so let's do another example. In this case, we're going to keep the resistance of each the same, just to simplify, okay? But we're going to do the same comparison that we did with series. So I'll do the first one, you guys will do the second one. All right, so for the first one here, we've got, thank you guys for appreciating this. Okay, we've got the 9-volt battery connected to 3 30 ohm in parallel. Here's my battery. There's my first 30, my second 30, my third 30. Like that. So, and again, this is 9 volts, and each of these is 30 ohms. So if we had to guess, At this point, it kind of seems like the equivalent resistance we get should be smaller than 30. Let's see what happens. Because the other thing is, what I'm finding here is the current through the wire just coming from the battery. Just this part. Be careful about that. From here and here. Anything in this part of the wire just directly with the battery, that is the current we're finding. Because when it gets into these paths, like we saw with the hill, it can split. So your total amount of current, it's like having a big water pipe, and then it splits into 3 other water pipes. You get a portion of the total current down each branch. We're not going to worry about calculating that. It gets a little bit more complicated, not too much more. You know what? I lied. I will show you how to do that calculation because it will help us compare to that video, but I'll show you. All right. So let's do this first. Okay. In order to find the current through the battery, I have to know how much total resistance the battery thinks it sees. So I need to find my equivalent resistance. That's my first step. All right, 1 over R parallel will equal 1 over R1 plus 1 over R2 plus 1 over R3. So that's going to be 1 over 30 plus 1 over 30 plus 1 over 30. Now these do have a common denominator, so I can divide, I'm going to say dividing by 30, then I have 1 plus 1 plus 1, which equals 3. All right, that tells me if 1 over R parallel equals 3 over 30, then I'm going to flip both sides, and R parallel will be 30 divided by 3, which is just 10. It is smaller. 10 ohms. Okay. Cool. Now that we know the equivalent resistance, and if you ever are not sure what I'm doing with this math, you can always let me know. I mostly do these fractions in my head because they're simple enough. Do not feel bad about plugging all of them in your calculator. Like fractions are fractions, right? So don't feel bad about just putting them in there and finding the numbers that way. Okay, so I have my delta V equals IR. I've got 9 equals the current that I don't know times 10. So my current will be 9 divided by 10, which is 0.9 amps. All right. That is the result so far for what we're doing. 3 resistors. Again, I want you guys to do this for 2 bulbs instead. Okay, so I'll draw it this time. You guys are doing this scenario like that, where you've got your 9 volts, you've got 30 ohms, you've got 30 ohms, and I'm gonna go rescue this cat who's getting himself stuck in the closet while you guys do this. Cecil, buddy, you're not supposed to go in there. Where did you go? There you go. Come on. Do you need help? Cecil is just in the closet. Oh. Hey, he opened the door. Okay. Okay, buddy. Go take it out. Thank you. No, Cecil. Okay, Frankie got 0.6 amps. That is what I got. Let's go through it to make sure everybody can get there. Okay. So, I'll do this in blue. I'll come over here. All right, so in this case, 1 over R parallel will just be 1 over 30 plus 1 over 30 because we only have 2, right? And then that is going to be 2 over 30. So R parallel will be the reciprocal of that, 30 divided by 2, which is just 15 ohms. Interesting. We have fewer resistors, and the equivalent resistance is bigger. That's going to be something for us to think about later. Okay. All right, now that we have our equivalent resistance, we can do our Ohm's law. So delta V equals IR. And again, we're using this Ohm's law right now for the entire circuit, but we can also use it for individual resistors, which we'll see. Okay, 9 volts equals I times 15. Divide both sides by 15, and that gives you current equals 0.6 amps. Now here's the thing. When I have more resistors, I have a smaller equivalent resistance, and I end up with a bigger current. That makes sense, right? Again, smaller resistance means like, yeah, send that current my way, no problem. A bigger equivalent resistance means a smaller current. But in the video, what we saw was that all of the bulbs stayed about the same brightness. And if anything, fewer bulbs might have been slightly brighter. But this current is smaller. Something is afoot, okay? And what that something is again, we only found the total current through the battery. We did not find the current through each light bulb. So let's do that now. Now what we're going to do is we know, we're now going to apply Ohm's law for a particular element, right? Because we know the resistance and we know the voltage, right? We know that up here, for one of these resistors, I'm starting at 9 volts and going to 0, and I have a resistance of 30, right? So I can use delta V just for R1. So this is the delta V across R1. It'll be the current through R1, and so we're going to use R1, right? So we're no longer thinking about the whole circuit, we're just thinking about this little element of it here, this little piece of it. All right, my delta V across is still 9 to 0, so I have a drop of 9 volts. I don't know the current, but I know that my resistance is 30, right? Because it's a 30 ohm light bulb. So if I divide both sides by 30, what I get, I hope I get the right thing, divided by 30, yay, 0.3 amps. Okay. So I have 0.3 amps that go through here. Like this total was 0.9. That was here. And now I know that I have 0.3 amps that go down through this branch. But like these branches are all the same. If I did an R2, my equation would look the same because the resistors are the same. So I also have 0.3 through that one and 0.3 through this one. And so what's really happening is it's like you've got a really big water pipe with your 0.9 amps, okay? And then we're splitting it into 3 equal water pipes, and they each get 0.3 of it. Right? And 0.3 plus 0.3 plus 0.3 would be 0.9. How much current goes through this 30 ohm resistor when there are only 2 in parallel? So here we have 0.6 coming through the battery. And how much goes through each of those? Frankie says 0.3. You're right. No question mark, 0.3. If we look here, again, we've got our 9 volts down to 0, and we have 30 ohms. It's the same as this equation again. 9 volts equals I times 30 ohms. We divide by 30, we get a current of 0.3. Because these resistors are the same. They're all 30 ohm resistors. Anytime you hook up a 30 ohm resistor to a 9 volt battery, and it's not in series, that's what you're going to get. So here, with this one, we have a smaller initial pipe of 0.6. So it's not quite as big as the 0.9, but then it only splits into 2 identical pipes, each 0.3. And again, this would be different if our resistors were different from each other, okay? And I mean, you can get into all sorts of hugely complex things. We're keeping it simple by having identical resistors, okay? The point is that you have some total amount that comes from the battery and then it splits. And when your resistors are the same, it will split in an even way. And what's really cool about this is all these resistors, no matter how many are in parallel, all get the same current as each other. So they're always the same brightness as each other. What? Doesn't matter if there's 2 of them or 5 of them or 10, they will all always get the same current. They will all always be the same brightness. As we add more bulbs, they stay bright. Okay. As we go from 2 to 3, they stay the same brightness. And then the other cool thing is we know that when we remove one, it stays lit up, right? The rest of them stay lit up. So let's draw that, my little remaining space. So I've got my battery here, I've got my resistor here. Okay, I've got these 3 in parallel, and now I'm going to remove one. Do I still complete circles, complete circuits? Yeah, I do. Through this one and through that one, I still have a connection from the top of the battery to the bottom of the battery. So they're fine, they stay on. They stay the same brightness. So the only thing that changes as we add more of these, the question is only for parallel. Yes, all of this stuff is just true for parallel, right? Again, series is like the opposite in behavior as parallel. So parallel circuits, I just think are really cool. They're really nifty. But something to really note, as we add more resistors, in order for them to each stay as bright as they were, we're going to end up drawing more and more current out of that battery. Okay, and that's going to be something that we'll talk about more in a second. Any questions about series versus parallel, or how to handle Ohm's law for these situations? I'm going to, while I wait for people to catch up to the lag and maybe have a question, I'm going to go ahead and erase though. All right. Okay, so actually here's a little bit of a mini quiz for you guys to make sure that you can check your understanding. So take a minute and sort these into whether they relate to series or parallel circuits. Okay, hopefully that's enough time. But let's go ahead and talk through these. Oops. All right, so the first one says, when you add another light bulb, all bulbs stay the same brightness. Okay, that was parallel. Okay, as we add light bulbs to the circuit, we draw more current from the battery, and then it splits evenly across the identical light bulbs, so they stay the same brightness. When we add another light bulb, they all get dimmer. That's going to be series, because when we add more, we're increasing the equivalent resistance, and so the battery there's less current being drawn from the battery. Okay, when we remove a light bulb, the others go out. That one is series, because once you remove something and you don't reconnect it, there's now a big gaping hole. There's not a complete loop. Will not be a good circuit. You don't get any movement of charge. So everything goes out. When we remove a light bulb, the others stay on. That one is parallel, because each other light bulb creates its own loop. That's the thing about parallel, is each resistor is in its own loop with the battery. E, the effective resistance increases as we add more resistors. That is going to be series, because as you add more, you're just directly adding more and more resistance. F, the effective resistance decreases. That's going to be parallel. That's that weird behavior where, because the way I think about it is, because we're giving the current options, that there's like less of a load on the battery. Like the battery's like, oh, this current can go anywhere, and so then the resistance, like, because it has more paths, it doesn't see as big of a resistance in total. Okay, G, the voltage across each resistor is the same, even if the resistors are different. Because you can build series or parallel circuits where this is true if everything is identical. But if they are different, you only always get the voltage across to be the same for parallel. Okay? Because they start at the top of the hill and they go to the bottom of the hill. And then H, the current through each resistor is the same, even if the resistors are different. So again, we saw with parallel that we had the 0.3 amps through all of them. That was only true because they were identical. If they were different, we're providing, the same hill with different choices. Do you want a lot of resistance or do you want a little? And so we get different current each way. But for series circuits, right, the current has no choice. It has to just go through that loop that goes through every single resistor, one after the other, to get back to the battery. Okay. Oh, I don't want it to be too big. All right, so now let's start talking about some of the practical things that have to do with circuits. There we go. So we've been talking about energy in terms of the energy of batteries. You might hear about electrical power, okay? Power, in general, is energy per time. So one of the places you may have heard of power is like horsepower for cars. So if you have a car with 100 horsepower engine, that's kind of pretty small, actually. And my Fiat had 100 horsepower that I used to have. Well, it's not very much. And what that means is that it takes a long time for that engine to convert its energy into the kinetic energy of the car. And it can take a longer time to speed up. But if you have like a really high-end like sports car, super fancy, it might have 700 horsepower or something. And it is much faster. It does a lot more energy per time. And so that car can speed up in a much faster amount of time. So that's one way to think about power. The other way with electricity is that usually we don't care about the total amount of energy that we get from a circuit. Okay, if I have a light bulb, I care how bright is that light bulb, right? How much energy do I get from it in this moment, but not over its whole lifetime. And so power is useful with light bulbs because it just tells you like every second how much energy do you get from it. And so a typical incandescent light bulb would be 60 watts. So capital W here is a watt. That is the unit of power. It's the same as a joule per second. Okay. So if you have a 60 watt light bulb, then every second you will get 60 joules of energy from that light bulb. How does it do that? Well, it's going to convert that energy from the battery into heat and light. And so the way we usually calculate this is, because again, this is not just energy itself, it's energy per time. So you can either say, well, here's how much energy the source gives us, and that would be, let me write it this way. So power from source, like from the battery, okay? We would have power P. Now your book uses the squiggly E, called the EMF. We didn't really touch on this much. EMF is kind of an inherent amount of voltage that the battery can generate. And there are slightly more details to that, but to be honest, I don't care. I don't need you guys to care. We can think of it as if we have a 9-volt battery, that one's going to be 9 volts. Okay? And then times the current. Okay, let's double check units real quick. This is measured in volts. And remember, a volt is a joule per coulomb. Current is measured in amps. An amp is a coulomb per second. Coulombs cancel, we have joules per second. That's our unit of energy. Okay. So this is how much energy the source gives off. We could also think about what is the power, and we use the word dissipated by resistor. So dissipated means it gives it away, it gives it off. Okay, usually through something like heat and light, which is what happens with light bulbs. Okay, and if we worry about that, then we've got the power will be I squared times R. And we're not going to prove that the units work. You'll have to trust me. They do. But the point is, power is related to brightness. And everything we've done before, during today, is I keep being like, oh, it's more current, so it's brighter. Yeah, it's more current, so it has more power, so it's brighter. Okay. All right. So again, I guess it's the same idea here. All right. So let's talk a few more practical things. One is that when we talk about a battery, it is an example of direct current. Okay? So DC stands for direct current. Okay, and basically what it means is a constant. Constant voltage. Okay, so if I were to map this through time, like if I look at delta V from the battery, for example, and here's time, it would look like this. A flat line. It's not changing. If I have a 9-volt battery, it gives me 9 volts. It gives me 9 volts now, it gives me 9 volts 5 minutes from now, or 10 minutes from now, or an hour from now. Now, eventually batteries die. That's going to be a separate thing that we're not getting into. Bring it up with your chemistry professors, okay? Because batteries are chemistry. But it's constant through time. So that is direct current. Now, if you plug something into an outlet of a wall, that's not what you get. Okay? Outlets in household circuits and in buildings and everything is AC. And AC means alternating current. And alternating means switching back and forth, right? You alternate this to that, to this to that. And what is it that we're alternating? We're alternating sign. So again, here's my delta V, here's time, and now it might look something more like this, where it looks like a sine or a cosine, but it's going from positive to negative, positive to negative. It's constantly switching signs. That's why it's called alternating. So a better picture is the one here, which shows the sine wave. We're going to talk more about waves later in the class, which should be a lot of fun. But the point here, it's not constant. Sometimes you get a really big voltage coming into your computer or your phone or whatever you have plugged in, or your TV. And then other times for a moment it might be 0. And then it switches direction and gets big and then it goes to 0 again. Right? And there are reasons why this is useful. But one of the biggest ones is actually that it's easier to get alternating current from a power plant to a building. If we relied on direct current, you would have to build a power plant like every block, because you just can't transmit it very far before it kind of dies away. But alternating current, there are kind of tricks you can play, which lets you transmit it miles and miles. Okay, so that's one of the big reasons. But what's interesting about this is that different places disagree on exactly what alternating current to use. So I have a couple examples here. In North America, your effective voltage, which is not the peak, it's 7/10 of the peak, is going to be 115 volts. Okay. In the frequency, and frequency tells you how often these waves come by, how often the peaks happen, is 60 times a second. So if you were counting, you would get 60 of these peaks every 1 second. Other places like Europe and China have a higher effective voltage, 220, like almost twice as much, and they have a smaller frequency. So if you're counting peaks, you would only count 50 of them. And ultimately, it doesn't much matter. Like, as long as you choose something and stick with it, it's fine. It's not like one's better or worse than the other. They're both fine, but that's why you can't just take electronics made for outlets here in the States and go to Europe and plug them in the wall. They won't work, right? Because they're expecting a different kind of electricity, so you have to have adapters. Okay. All right. So what are some of the dangers of electricity? Electricity is undoubtedly dangerous. Like, it's also useful, right? Clearly, we wouldn't be having this remote, class internet, computer, lights, and anything without electricity. It's definitely useful. It can also be dangerous, right? And one of the reasons I wanted to show you this is to give you a sense of different amps, right? So different sort of levels of what is this current and what does that mean? Okay, so this was a graph I found from a website that's listed below, but a tingling sensation, so when you start to feel it, would be about 1 milliamp. So a milliamp would be like 0, so this would be 0.001 amps. That's oh, you can't see that. That's a milliamp. Okay. That's pretty small. It's not, and it's also not very dangerous. But then 5 milliamps is the maximum harmless. So you get like a static shock or something where you're like, oh, you get zapped. It's probably way less than 5 milliamps. If you get much bigger than that, you're still in the milliamp range, which is still pretty small. 10 to 20 milliamps, this is the can't let go current. So this is one of the things that's really dangerous, and it has to do with the way our bodies biologically work in terms of muscles, right, are controlled by electricity. We have electricity in our brains, and the nervous system sends electrical current through our bodies to communicate signals and do things like tell your hand what to do. And the problem is that those signals say grab. Okay? That's like the default. And as you overload with more current, all your muscles are being told to do is grab harder. So if you're like an electrician or you're working with electric wires and you grab onto a live wire, something with electricity running through it, this is the can't let go thing, where the electricity is telling your hand, hold on and hold on tighter. And the tighter you hold on, the more dangerous it is. So that's one of the problems. It's not just the current itself, but it's our actual response to that current. Okay? And then as you get even higher, it can do, worse things. So even into the 100 and 300 milliamp range, so this is way less than 1 amp, can still be fatal because it disrupts our body systems, right? Our body communicates with itself through electricity. And so receiving electricity into your body disrupts all of that, sometimes to a bad degree. The other issue you can have with electricity is it carries energy. And as it carries energy through your soft, delicate tissues, they can get burned. Okay? So my recommendation is try not to get hit by lightning. Try not to touch live wires. This is why it's really important if you ever do work with electricity stuff that you always, always, always make sure that those power sources are off, right? Never work with live wires. It's very dangerous. Okay. I did want to show you, though, a situation which is less grim and more interesting, which is working with a lot of lightning-like electricity safely. So we'll make this bigger. This is Adam Savage. If you've ever watched the show Mythbusters, which is one of my favorites. And I think there's like music with this. All right. I think that's the, I think that was the Doctor Who theme, maybe. The point here, oh, yes, thank you, Frankie. I even found it to begin with. I was going to show it. Frankie's asking about the quiz codes. Thank you for reminding me. Because I looked it up beforehand. I'll double check, but I'm pretty sure that I remember what it was. Yes, I'm right. 33313. Okay. All right. So in this video, we got Adam Savage, and he is surrounded by a metal cage, and outside of that is a Tesla coil. And actually, if you've ever been to the Griffith Observatory, like the museum part inside, they have one of these. And it's basically a lightning machine. Okay, so it can generate this huge, like what shows here, this huge visible spark of electricity, because the way it does it is it creates an enormous electric field. Okay, and that electric field pushes the charges, and they all can get pushed through the air to some place, right, some spot. So obviously, I just told you guys, don't get hit by lightning, right? This is a lot of current flowing through the air, and he's perfectly safe because he's inside this metal cage. Okay? And what this is called a Faraday cage. And it actually works on the principle of something we talked about last time, with a couple times ago with electrostatics, which is that when you have a conductor, and metal is a conductor, any extra charge always goes to the outside. So if you are inside that metal, the extra charge never comes where you are. You're safe. It's only on the outside surface that things are dangerous. So as long as he stays inside that metal cage, no amount of this huge sparking and almost lightning-like stuff is going to hurt him, right? Which I think is pretty cool. They'll do the same thing actually with microwaves. If you look at a door of a microwave sometime, at least the old-fashioned ones, I don't know if more modern ones, if they hide it better, but sometimes you could see like little like lattice kind of look like that sort of thing on the microwave door. And what that is, you've got the glass, and then they put tiny little wire, metal conductor wire, around the whole thing. So a microwave oven has a Faraday cage in it, so that the electric fields that are being created by the microwaves, which we'll talk about more later, I feel like I say that a lot, but we talk about lots of cool stuff in this class. They don't escape. They stay trapped inside the microwave. So it's almost the opposite of this one, where you can essentially use Faraday's cages to trap things. Another example of this, if you ever, I don't know how many of you would do this, but if you ever, sometimes when you order like finicky little electronic stuff, it will come in like a foil bag. And that foil bag is a Faraday cage, and it protects like the delicate electronics from stray electric fields. Nothing gets inside the metal bag, which is pretty cool. All right. So that brings us to kind of the last thing here, which is talking about circuits inside like something like a house. And this is from your book. There's a table that has a couple different appliances and what kind of power they consume, right? So again, power is the energy per second, measured in watts. And so you've got stuff like real big energy things are like a stove or a clothes dryer or water heater or a washer, a dishwasher. Like those will kind of make sense. They have to use a lot of power. I think what always surprises me here is how much the coffee maker might use. And then something like a TV is actually relatively really small, which I think is interesting. There are also the currents. And you'll note here, all of these currents are way above that danger zone that we talked about before of a few milliamps, right? This is like 27 amps. So again, don't touch wires in your house if they're live. Okay, question. What if he touches the cage from the inside? As long as you touch the inside surface, you're okay, but you don't want to reach around and touch the outside surface. So it's safer to like not touch the walls just in case. That's a good question. I like that question. Okay, so the last thing is that generally in a house or any kind of building, circuits are always built in parallel. And there are a couple of reasons for that. One, if I turn off the TV, I don't want everything else in my house to not be able to turn on, right? If we built these in series, anytime you turned one thing off, everything else would stay off. You'd have to have everything turned on at the same time to have anything on. That seems like a bad idea, right? So you do it in parallel. That way you can turn a light on and have the TV off, or vice versa. But there's a danger, right? We saw with parallel circuits that as we add more resistors, we draw more and more current from that power supply, right? So it's not a battery for a house. It comes from a power plant, usually, unless you like live off the grid and have a generator or solar panels or something. But in any case, you've got your voltage source and you draw more and more current from it. And as you draw more current from it, you're more and more likely that those wires get heated up, okay? And that's how you can start fires with electricity, is when the elements draw too much current and they heat up too much, right? Because the power dissipated depends on current squared. So even if the resistance of the wire is small, which it would be, if it draws enough current, generate enough power, could catch on fire. So that's a fire hazard, and that's why they make circuit breakers. So a circuit breaker is a weak point in a circuit that you want to put next to the power supply. So the circuit, you've got your power supply, and you've got your circuit breaker before you get to any parallel branches for your appliances. And it has to be a weak spot because it needs to fail first. You want your breaker to fail before the thing draws too much current and catches on fire. And so that's why safe practices for these things is to have that circuit breaker there. So if you draw too much current, it snaps it. Now it's open. You can't turn anything on, which is like really annoying, but it's also safer. And then you can reset the breaker and try again without drawing as much current. And so people who try to bypass that by putting like pennies in the old style breakers were just, willing their house to set on fire, I suppose. It's a bad idea. Very bad idea. All right. Is there anything else? Yeah, that's all I've got for you guys. So are there any other questions about electricity in general, its use, or kind of the effects on us? Oh no, it says there's a network error on my side. All right, well, I'm gonna go ahead and stop it here. So if you guys do end up having questions, as always, feel free to find me on Discord. All right, see you another time.